Well, hey everybody, we're going to continue with part 3 of our questions. This is going to be questions 29 through 30 for our gas laws intro. So let's see, we left off at question 28 before. Better zoom out here a bit. You can see this. Okay, have my periodic table next to us. All right, so let's see, question number 29. Zoom out, add more. What is the heat of fusion of water? Now, that's the amount of heat that it takes to melt or freeze 1 gram of liquid. So you come over here. The heat of fusion of water is on your periodic table. You can see is 80 calories per gram. 80 calories per gram. Or in joules, you've got it right there. Specific heat of water. Make sure I'm answering the right question. Oh, wait a minute. My mistake. Heat of fusion of water. There we go. 334 is what the amount of joules will be. 334 joules. What's the heat of vaporization of water? So this is the amount of energy it takes to boil, to boil or condense 1 gram of water. And when we take a look, we got to look at heat of vaporization. 540 calories. Wow, look at that. A lot more energy to change this into a gas or to change it from a gas back into a liquid. And in joules, 2,260 joules. So that's just looking on your periodic table. You'll have this referenced on there. How much energy is needed to melt 500 grams of ice at 0 degrees? Let me zoom out. So when we're working on that, we're working on this first part right here. This is where freezing or melting occurs. So how much energy? We're looking for Q equals to melt. Okay, the opposite of melting is freezing. So we're going to need to use the equation. Heat of fusion is going to be Q equals mass times delta heat of fusion. Mass times delta heat, change of heat of fusion. The mass given here is 500 grams. We need to multiply that by the heat of fusion of water. And we want to do this in, does it say, okay, it's not asking whether we want it in joules or, so I'm just going to do, let's see, heat of fusion of water. We can multiply it by 80 calories per gram. Now, on the test, if all the answers are in joules, you'll want to substitute 334. The grams cancel out, and this will tell you can do the math yourself. I'm not going to do it for you. So you'd want to use this equation because when you've got melting or freezing, you're at this part on your graph, and there is no delta T. You cannot use MCAT. How much energy is needed to vaporize, boil? Now we're talking this part of the graph, 500 grams of water at 100 degrees. Okay, well the 100 degrees is just telling you, okay, you're right over here at the boiling or the condensing point. So that's just extra. You don't need to really use that because we told it we're boiling. So we're going to need Q equals, and since we've got this going on, it'll be Q equals mass times delta heat of vaporization. Q equals the mass times change in heat of vaporization. And the mass in this problem is 500 grams. This you don't need to use. It's just telling you, it's just confirming that, yeah, we're boiling something. Oh, okay. And let's see, the heat of vaporization. I'm just going to use the calories since it didn't say, times 540 calories per gram. Now let me see here. We're boiling. So you got to ask yourself, once you get your answer over here, and the answer will be in calories, you got to ask yourself, is it a plus or a minus? If we're boiling water, we are adding heat to it, and so that means it's endothermic. It'll be a plus. I forgot to do this on number 31. Let's look back to 31 here for a moment. So we've got, let's see, 8 times 5. Okay, it's going to be 4,000 or something like that. Anyway, 35. Anyway. You got this number here, but is it plus or minus? If we're melting, if we're melting ice, yeah, we're adding heat into it. So the answer is going to be a plus number because we're adding heat into this chunk of ice. If this was freezing, we would have had to make this a negative value. If this one was condensing, because condensing is taking heat away from the steam, we would have had to make our answer negative. Let's see, number 33. During a phase change, what happens to the temperature of a substance? Well, on our chart here, we've got two phase changes listed. We've got this one right here, the flat parts on this graph. This would be, if we're going this way, melting. If we're going that way, freezing. Over here, if we're going this direction, we have vaporizing or boiling. If we're going that direction, condensation. So, what happens to the temperature? That's a flat line. There's no change in temperature. No delta T. It's taking a lot of energy to break the bonds that if these are solid melting, or it takes a lot of energy to pull the atoms apart if you're trying to boil it. So there's no change in temperature. How many calories are in a food calorie? Well, let's see. 1,000, that should be little c calories equals 1 big C calorie. And I've asked you on your periodic tables, I have these annotated and marked on there. 1,000 little c calories equals, that almost looks like calozone, calorie, i.e., there we go, which is the same as 1 kilocalorie with the lowercase calorie. That just means 1,000 calories, which equals 1 food calorie. Okay, so there you go. You look on your bag of chips, this particular bag of chips, big C, there's 140 kilocalories or food calories in this. Number 35, when calculating heat, if Q is positive, it means heat was, okay, so first off, we got to go back to our system. We talked about this with the mousetrap. Okay, the system, if we're putting heat into the system, we're adding heat, energy is entering, energy entering is endothermic. If we're taking heat out of the system, if energy is exiting, that's exothermic. And we're taking heat away, that's negative. So when calculating heat, if Q is positive, over here, it means heat was added. I guess we're going to say heat was added. Or energy was added. And delta T is going to be positive. See that over there? Because we were adding heat, and because we're adding heat, the change in temperature will be positive. When calculating heat, if Q is negative, okay, that means we're pulling heat out, energy is exiting the system, heat was lost, and delta T will be negative because we're taking heat away. Let's see. Oh, yeah, okay, got that one done. So I used the same. When using the equation Q equals MCAT, what does Q represent? Well, you better know it. Q represents, Q equals heat, lost or gained. And you can either measure it with calories, big C calories, known as a kilocalorie, or you can measure it with joules. That's the units for heat. Now it says label the graph above, include arrows to show endothermic and exothermic. Well, let me see. We've spent a lot of time in class working on that. On page 13 in your notes, assignment number 13, you should have this diagram. I'm not going to take a lot of time to go over this diagram right now, but you've got this in your notes. But include arrows to show endothermic and exothermic. So let's see. If we're adding heat, that's endothermic. On this chart here, this is representing that we're adding more heat over here. So if we're going this direction, it's a plus Q because we're adding heat. And that's called, if we got a plus Q, energy is entering the system, it's endothermic. And over here, if we're going this direction, if we're taking heat away, because as we go down this graph, you can see the temperature is getting smaller. So heat is exiting, heat exits the system, which means we've got a negative Q. And since it's exiting, it's exothermic, to give it a label. So that's as much as I'm going to go into there. You need to go through and label solids, liquids, gases. This direction, is it going to be melting or freezing as you add heat? Is it melting or freezing as you take away? You can do that, and you can look at your chart that you made there on page 13. And what is the kinetic theory of matter? What does it say about gases? Well, let's see. The kinetic theory of matter, first off, says matter is made of, of moving particles. Well, we'll say moving atoms. They can even be molecules, but we'll just say atoms because it's shorter. When we draw our diagrams for a gas, we show them very far apart. For a liquid, we show them that they're close together and that they can move a little bit. Oh, these guys, we should put large arrows showing that they are moving fast and in straight lines. Liquids kind of move around a little bit. Now, solids are locked into a pattern. They cannot move freely. They can vibrate. I'm trying to make these look like just a little like they're vibrating. So they're locked into a pattern. So solids are really close together. Liquids are close together, but they can move freely. Free moving. That makes them technically a fluid. Both liquids and gases is a fluid. Let's see. If you increase the temperature, you will increase their speed. They move faster, which is speed. And the fancy way to say that is you're increasing their kinetic energy. Gases have low density. Liquids and solids, high density, or at least higher density than gases. Oh, let's see. I think that's just about everything. The atom spacing. These guys got more energy. So I think that's just about it on that. Let me verify in our notes here, because I'm just going back to our notes on assignment number. Let's see. Was that page 11? Kinetic. Yeah, move faster. Straight lines. Okay. I think we said for gases we assume gases are not attracted to each other. Gases are not attracted to each other. They're all surrounded, all atoms are, with negative electrons, and those negative electrons want to be far apart. All right, there we go. We're done. Bye.